Hi guys, welcome to this third part of Lecture 6, where what we're going to do is put all that stuff we've just been talking about to use and think about some semantic notions with regards to first order logic. So specifically, right, now that we've defined truth in FOL, we can use it to make sense of a number of relevant semantic notions. Now note that these notions are going to be very similar to the ones we defined for TFL, but there's a really deep fundamental difference. Everything with regards to these semantic notions we defined for TFL was characterized in terms of valuations. Nothing that we'll talk about with first order logic has to do with valuations. Those are done. Those only apply to TFL. Everything that we're going to talk about with regards to FOL is going to be defined in terms of interpretations, the things that we've been talking about for the previous parts in this lecture. Now note, as with TFL, we're going to use the double turn style, and this is again going to represent entailment. However, when we're thinking about FOL, this isn't going to be defined in terms of valuations. It's just like everything else going to be defined in terms of interpretations. So let's start to put some of this to use, right? Let's say first, right, with regards to entailment, some sentences A1 through AN are going to entail some sentence C if and only if there's no interpretation in which all of the initial sentences are true and the C is false. So it's just like with the TFL notion of tautological entailment, right? But instead of defined in terms of valuations, it's defined in terms of interpretations. Again, entailment will hold if and only if there's no interpretation that makes our initial sentences true and our final sentence false. Of course, this is going to line up just like before with some notions of validity and non-validity. Right? So we can say that an argument, A1 through AN, therefore C, is valid in first order logic if and only if there's no interpretation in which all the premises are true and the conclusion false. Similarly, an argument A1 through AN, therefore C, is invalid in first order logic if and only if there's some interpretation in which all the premises are true and the conclusion false. So again, we've got this lovely notion of validity we're recovering back. Right? Using interpretations, we can now settle whether arguments are valid or invalid. We just see if we can come up with an interpretation that makes all the premise sentences true and the conclusion false. If we can, the argument's invalid. If we can't, in fact, if in every interpretation that makes the premises true, the conclusion's false, then we know the argument's valid, or at least valid in first order logic. So that's our first notion. Another first three notions. Our second pair of notions are kind of familiar. And again, these are going to roughly parallel some notions we defined for TFL. So we'll say that an FOL sentence A is a logical truth if and only if it's true in every interpretation. And we can write it like so, right? We can write a double turn style with nothing on the left and then our sentence A on the right. So a notion of logical truth is very similar to, in fact, perfectly parallels the notion of a tautology. But a notion of tautology was defined in terms of valuations, and this is defined in terms of interpretations. So this is basically the notion of tautology that applies to FOL. Similarly, a first order logic sentence is a contradiction if and only if it's false in every interpretation. Now, we'll just use the same word as we did in TFL, but again, this concept is going to be defined in terms of interpretations. Again, this notion of logical truth and contradiction is very similar to the notion of being a tautology or being a contradiction that we defined in TFL. Another pair of notions we can also define. We can say that some sentences A1 through AN are jointly consistent if and only if there's an interpretation in which all are true. And A1 through AN are going to be jointly inconsistent if and only if there's no interpretation on which they're all true. So these are very similar to jointly tautologically consistent and jointly tautologically inconsistent, but they're not the same. And again, they're not the same because these two notions are defined in terms of interpretations, where our previous notions were defined in terms of valuations. So these are notions that apply to FOL sentences, not to TFL sentences. Similarly, the previous notions of joint tautological consistency and joint tautological inconsistency apply to TFL sentences, not first-order logic sentences. Cool. Now what's neat, and this is why we actually want to go in for this stuff, is that we can use interpretations to test for these various semantic properties. For example, to show that some sentence is not a logical truth, all we have to do is find an interpretation where the sentence is false. On the other hand, right, to show that the sentence is not a contradiction, all we have to do is find an interpretation where the sentence is true. Now, I said find, and that's actually kind of misleading, because what we're not going to do is go, dig around and see if we could find an interpretation. Instead, what we're going to do is we're going to construct interpretations. And we're going to construct interpretations to show what we're after. And we're going to construct interpretations by specifying 3 parts. First, we're going to set on a domain. We're going to say, hey, this is the domain I want to talk about. Then we're going to fix the denotation of relevant names. If there are any names relevant, then we'll say, hey, this name picks out this object in the domain, this name picks out that object in the domain, and so on. Right? And finally, and most importantly, we're going to stipulate the extension of relevant predicates. We're going to say, hey, cool, now in this domain, these are the things that this predicate applies to. Again, remember, we have 2 ways to do this. We can either do it indirectly or directly. So let's talk about it. Let's think about some few examples, right? So let's take this sentence. It's an existentially quantified sentence that says, hey, if there exists something that will make this conditional claim true. If that thing's an F, then A equals B. So let's show that this sentence isn't a logical truth and isn't a contradiction. So to first show it's not a logical truth, we need to construct an interpretation where it's false. And note, when you're constructing interpretations, you have free reign. You can set the domain to whatever you want, as long as it's not empty, right? You can set the extensions of our predicates to anything you want. Remember, they can be empty, they can be universal, or they can be just a few things. And you can set the names to pick out whatever you want in your domain. So for example, here's a simple interpretation. Our domain is Robin Hood, in fact, the best Robin Hood, in my opinion, and Fantastic Mr. Fox. We'll have our predicate be is a fox, so we're going to settle this indirectly. Of course, as it happens in this case, the predicate applies to everything in our domain. Okay. And we'll have A pick out Robin, and B pick out Fantastic Mr. Fox. Now on this interpretation, our sentence is false. And why is our sentence false? Well, because in fact, there's nothing that we can plug in place of X that will make the antecedent true and the consequent true. Consequent is always false because Robin and Fantastic Mr. Fox are different individuals. Consequent's always false, and hey, as it happens, every single individual we plug in is going to make the antecedent true. So antecedent's always true, consequent's always false, which means this is always false, which means there's nothing in our domain that will make the existential true. So this sentence is not a logical truth because we can construct an interpretation that makes the sentence false. Now, what about the other way? So we've shown that it's false in one interpretation, but is it a contradiction? Well, let's show that this sentence isn't a contradiction. That is, let's come up with an interpretation where it's true. So here's my sample interpretation. Our domain is just Robin. It's Robin by himself. Right? Our predicate is going to again be is a fox. So I'm stipulating it indirectly. But in this case, again, it is satisfied by everything in our domain because we have a very small domain. Right? And for the 2 names, we'll have A pick out Robin Hood and B pick out Robin Hood. And this highlights something nice when you're constructing interpretations. Remember, the restriction is no empty domains and no empty names. But no empty names doesn't mean that we can't have multiple names for one object. And similarly, no empty domains doesn't mean that we can't have a domain with only one thing in it. Okay? So on this interpretation, our sentence is true. Why is our sentence true? Because our consequence is true. So no matter what we plug in here, this conditional is always true. Of course, as it happens, no matter what we plug in here, everything in our domain, we can start plugging in anything you like. Of course, it's always just Robin, and Robin is a fox, and Robin is identical to himself. So we can find something in our domain that will make this conditional claim true, which means our existential claim is true. So on this interpretation, our sentence is true. Now, I highlight these just to kind of give you a sense, one, of how to go about constructing interpretations, and two, to show you what it is we're aiming at when we're trying to show a sentence is or is not a contradiction and is or is not a logical truth. We've just demonstrated that this sentence isn't a logical truth by constructing an interpretation where it's false, and we've shown it's not a contradiction because we constructed an interpretation where it's true. So cool, right? You know how then to approach questions like if I say, is this sentence a logical truth or a contradiction or neither? You can go through and show me if it is or isn't some of these. Or at least I've shown you how to show that it's not. Now let's think about some of the other properties, right? So suppose we've got two sentences, A and B, and we want to show that they're not logically equivalent. To do this, what we need to do is find an interpretation where our sentences differ in truth value. Right? So let's take these two, for example. We've got a universally quantified claim, right, for all x, fx, or gx, and an existential quantified claim. There is something such that fx or gx. Now what we want to do is we want to show that these are not logically equivalent. That is, there's at least one interpretation where they differ in truth value. So let's go ahead and do that. Let's offer the following interpretation. Right? So we'll have our domain. Our domain is Jake the dog, and again, the best Robin Hood. Right? And we'll think about our two predicates, F and G. Right? So let's directly stipulate the extension of this, of F is Robin, and the extension of G is empty. That is, G isn't satisfied by Jake or Robin. It's not satisfied by anything in our domain. Now, what's nice is that on this interpretation, the universally quantified claim is false, or our existentially quantified claim is true. Now, why is that? Well, let's go with the existential first. So our existential says, hey, there's something in the domain that's either an F or a G. And there is. Robin. Robin's an F. Robin satisfies the predicate F. And he doesn't satisfy the predicate G, but that's okay, because this is a disjunction, and in order to satisfy this sentence, you only have to at least get one of the two. So we can plug Robin in place of the X here. We get, F Robin or G Robin. Of course, F Robin's true, so our disjunction's true, and that means there's at least one thing in our domain that'll make this existential true. In contrast, let's think about the universal. The universal says, hey, everything in the domain is either an F or a G. And of course, this claim will be false if there's at least one thing in our domain that isn't either an F or a G. And that's Jake. Because Jake is not in the extension of the predicate F. So if we plug in Jake for X, this side will be true, or this side will be false. And similarly, Jake is in the extension of G, because nothing's in the extension of G. So if we plug in Jake this side, right, well, G Jake is also false. So F Jake's false, G Jake's false. That means there's at least one thing that makes this disjunction false, at least one thing in our domain that makes this disjunction false, which makes our universal claim false. So this little interpretation shows that these two sentences are not logically equivalent. There's at least one interpretation where they come apart in truth. Now note, something funny about my interpretation is because of the sentences I was looking at, I didn't need to specify any names. And that's because the sentences just didn't feature names, so I didn't need them in my interpretation. I could get by just by saying what the domain was and by specifying the extension of the predicates. Good. So this shows us how we can use interpretations to think about logical equivalency, specifically to show that some sentences are not equivalent. Now let's think about the last one, right? Suppose we've given an argument and we want to show that the argument is invalid. Well, to show that the argument's invalid, all we have to do is find one interpretation, right, where the premises are true and the conclusion's false. Where the two halves, if you like, differ in truth value. These are all true and this is false. So how are we going to do that? Well, let's take this argument. And we're going to show that this argument has got a one premise and a conclusion is invalid. That is, it's possible for all the premises to be true and the conclusion false. We're going to do it by constructing an interpretation where premise is true and conclusion's false. Right? So let's do it. We're going to use Jake and Robin again. Here's our interpretation. Our domain is going to be Jake and Robin. Our only predicate, which is F, we're again going to directly stipulate the extension. The predicate F, the extension is going to be Robin. And in this case, our name A, we're going to have A pick out Jake. So here's our interpretation. Now on this interpretation, let's start with our conclusion. Our conclusion is false. Now why is our conclusion false? Well, first thing to note is what's the main operator of this sentence? Well, it's the conditional, right? So, right, cool. This conditional is going to be false if we have a true antecedent and a false consequent. So is our consequent false? Well, the name A picks out Jake, and FA will be false if Jake isn't in the extension of F. He's not. So consequent is false, right? A is not in the extension of F, so FA is false. Okay, what about the antecedent? Well, the antecedent's true. Why is the antecedent true? Because there's something in our domain that's an F, namely Robin. That is, there's something in our domain that's in the extension of the predicate F, which is what our antecedent says. So our antecedent's true, our consequent is false, which means the conditional claim's false. So on this interpretation, conclusion is false. But now here's the weird thing. Our premise is true. Now why is our premise true? Right? So the main connective of our premise is this existential. So we need to make the existential true in order for the premise to be true. Now what does the existential say? It says, hey, there's something that you can plug in place of X that's going to make this sentence inside the brackets true. Now, in this case, we only have two things, so it's helpful, right? We can just literally try them out and see what happens. So let's plug in Robin for X. Well, F Robin. Yeah, Robin's in the extension of F, so our antecedent's going to be true. Oh, crap. But our consequent's false because A picks out Jake, and Jake's not in the extension of F. So when we plug in Robin, right, this conditional claim is false, just like over here. But what happens when we plug in Jake? Well, if we plug in Jake for X, we get F Jake, which is false because Jake is not in the extension of F. So our antecedent's false. And hey, this is a conditional. So any conditional with a false antecedent is true. It doesn't matter, of course, that the consequent here is also false, right? We've made the antecedent false, and hence there's something that makes this conditional false, this conditional true. So the upshot is there's something in the domain that will make this conditional claim true, namely Jake. Why? Because Jake makes the antecedent false, which makes the conditional true. So on this interpretation, our premise is true, and our conclusion is false. And the upshot then is that this argument, which seems prima facie plausible, turns out to be invalid. We've also learned something else too. This interpretation shows us that these two sentences are not logically equivalent. Right? But importantly, what we've done is we've constructed an interpretation, right, where it makes all the premises true and the conclusion false, and hence shown that the argument is invalid. So this again highlights what we can do with these interpretations, right? We can show that a sentence isn't a logical truth. We can show that a sentence isn't a contradiction. We can show that some sentences aren't logically equivalent, and we can show that an argument is not valid. That's pretty cool, right? In fact, we can also do this diagrammatically. So here's a different argument, right? And we can show that this argument is also invalid, and we can do so in this case by constructing a diagrammatic interpretation. So again, to show this is invalid, what we need to do is make the premise true and the conclusion false. So our premise is, hey, for everything in the domain, there's something that it ems. And our conclusion says, hey, there's something such that everything in the domain ems it. Okay. So let's construct an interpretation. Again, when we're doing diagrammatic interpretations, we don't need to specify a domain because we can just, the nodes that we mention in our diagram are the things in our domain. We don't really need to specify names because we can just simply label the nodes, right? And we don't really have to specify extensions. Instead, we can use our arrows to say these are the relevant ordered pairs. Right? So here we have the ordered pair MAB, MBC, and MCA. Those three sentences are going to be true in this interpretation. Now note, what does this mean? It means that our premise is true. Because I just told you, right? We can plug in every single name in place of X, and there'll always be at least one name we can plug in place of Y to get a true sentence. If we make A in for X, then we can plug in B. If we plug in B for X, then we can plug in C for Y. And if we plug in C for X, then we can plug in A for Y. So this sentence is true on this interpretation. In contrast, our conclusion is false. Right? Why is our conclusion false? Because a conclusion says, hey, there's some name we can fill in here in place of Y, and once we do that, we can then fill in every name in the domain in place of X and get a sentence that's true. So let's try it. Let's plug in A for Y. Well, now what we have is for all X, MXA. And is that going to be true? Well, no, because we can just plug in B for X and get a false sentence, because it's not true that MBA. Okay. So it's not going to work when we use A. Similarly, if we plug in B for Y, right, then again we'll get for all X, MXB. Right? But of course, then we can just plug in C for X and we get something false, because it's not true on this interpretation that MCB. The arrow goes this way, not this way. And the same thing is going to be true for C. We can plug in C for Y, and then of course, right, we're going to be able to plug in, say, A for X and get a false sentence. So on this diagrammatic interpretation, the conclusion here is false. So this interpretation shows that this argument is invalid. It's kind of cool, right? We can even construct interpretations like this, which will now show us whether an argument is valid or invalid. Well, that's strictly not true. All we can do is construct this to show that the argument is invalid. So that's neat. And this is something we can do with these interpretations. This is really powerful. So one interesting upshot, if you probably clocked it thinking about the relationship between some of these properties, is that if we have some interpretation that makes all of A1 through AN and C false, right? Sorry, we makes all of A1 through AN true and C false, then we'll know that this argument is going to be invalid, again, because these will be true and that false. that A1 through AN doesn't entail C, because there'll be some interpretation where these are true and that's false. And finally, if we can do all of this, then we'll know that A1 through AN and not C are going to be jointly consistent, because we'll have come up with some interpretation that makes all of them, if we add the negation to C, true. Now, just to put some terminology here, an interpretation that refutes a claim is called a countermodel. When we're thinking about first-order logic, we're almost always going to be aiming to construct countermodels. That is, we're going to be showing that an argument is invalid, that an entailment does not hold, that a sentence is not a logical truth or is not a contradiction. And finally, that some sentences are not logically equivalent. And this is actually interesting, and it stems broadly from something about the way of interpretations work. But before we talk about that, a little bit of pragmatics about constructing interpretations. So, constructing interpretations is something you get used to as you practice it more. But there are some practical suggestions. So first, when you're constructing them, keep your domain small. This makes it easy to specify what the predicates will be true of, and very easy, if you're dealing with quantifiers, to just sort of literally trial through with every single object. Small domain makes it easy to do that. Second point is remember that you can directly and indirectly specify predicate extensions. In particular, it's very handy to be able to just simply stipulate directly, these guys are going to be an extension of this predicate and this one isn't. Thirdly, remember that predicates can be true of all or none of the things in your domain, especially the none, right? Being able to make a predicate empty is incredibly useful sometimes. So keep that in your back pocket. Remember you can do it. And then finally, if you're thinking about two-place relations, consider constructing diagrammatic interpretations. Those are often helpful, especially if you're a spatial thinker. So that's really the big things with regards to using interpretations to understand these semantic notions. I want to end with a final, possibly ominous point, and it highlights something I mentioned a second ago. Right? Everything I just told you about how to use interpretations was broadly constructing countermodels. I told you how to show that a sentence isn't a logical truth, isn't a contradiction, that some sentences aren't equivalent, and that an argument isn't valid. What do we do if we're going to show the other way? What will we do to show that a sentence is a logical truth or that it is a contradiction? Well, then we have to think about all interpretations, literally every possible interpretation. And in fact, the same is going to be true for some other features too. So if we want to show that two sentences are logically equivalent, we then have to think about every possible interpretation. The same thing for some sentences being jointly inconsistent, or that some sentences entail some sentence C, or even that an argument's valid. Because remember, especially with these last two, what we're really claiming is that there's absolutely no interpretation that will make A1 through AN true and C false. And this requires thinking about every possible interpretation. So if we're thinking about this a little bit more, right, we have something like this table. If you've got a sentence and you're asking whether it's a logical truth or a contradiction, to show that it is requires thinking about every possible interpretation. To show that it isn't, all you need to do is construct one countermodel. Similarly, if you've got some sentences and you want to show that they're equivalent, you've got to think about every possible interpretation and somehow show that on every interpretation, they always have the same truth value. Meanwhile, to show that they're not equivalent, just one countermodel. When it comes to consistency, you can show that some sentences are consistent by giving one interpretation where they're all true. To show that they're inconsistent, however, you need to somehow think about all possible interpretations. And finally, when we think about validity and entailment, again, to show that the entailment holds, the argument is valid, you need to think about all possible interpretations. To show that the entailment doesn't hold, the argument is invalid, just a single countermodel. Now that might not seem that weird, right? So cool, I talked to you, I showed you how to construct these sorts of things, like construct interpretations, so countermodels, or maybe an interpretation that make a bunch of sentences true, right? But what about the cases where we have to think about all possible interpretations? Well, the problem is, in those cases, we're kind of screwed, right? To put it slightly less bluntly, right? In those cases, we have to think about all possible interpretations. And what this means is that we can't just sit there and construct as many interpretations as we possibly can. Because no matter how many we build, it's never going to be enough. We've only ever considered some of all the possible ones, not every possible interpretation. So what this actually means, if you go back a slide, is that in the cases where it says all interpretations, we don't have a tool yet that helps us do this. We can't use interpretations, at least not constructing them, to show that an argument is valid, to show that an entailment holds, to show that some sentences are inconsistent, to show that some sentences are equivalent, or to show that a sentence is a truth, a logical truth, or a contradiction. Those are beyond our capacity with regards to constructing interpretations. And again, the reason why is because all we can do is construct a finite number of interpretations. But we need to think about every possible one. So what do we do in those cases? Well, to be honest, the best we can really do is construct arguments in our meta language. That is, we can say something in English, which will then let us talk about all interpretations. So for example, here's an argument. Right? It's got, there is something such that it's an F and a G, then there's going to be something that's a G. Now it's clear that this argument's valid. Right? If there's something that's both an F and a G, then that thing's definitely G, because it's both F and G. But we can't construct all the possible interpretations to show that this holds. The best we can do is to think about this in the kind of meta language level, i.e. talk about it in English, at least for the moment. So I might offer you something like this, right? Take any arbitrary interpretation in which the premise is true. Right? In such a case, you can extend the interpretation with a new name A that will make the embedded sentence true. Right? And of course, if FA and GA is true, then GA is true because it's a conjunction. Conjunctions are only true when both conjuncts are true. Now, since GA will be true, we know that if GA is true, then there's got to be something in the domain, namely A, that's a G. So from GA, we can go to this existential claim. Right? Now here's the kicker. Because we didn't say anything about our original interpretation, other than it's one where the premise is true, it looks like we can run this exact same reasoning on every interpretation where the premise is true. This is because what we did is we picked an arbitrary interpretation. So it could have been any of the ones that satisfy this property of the premise being true. So it looks like in every interpretation where the premise is true, we'll be able to run this kind of reasoning and get out this conclusion. So it looks like for all interpretations where the premise is true, conclusion is true. Hence the argument's valid. Problem, this is all in the meta language. We want to find some way to formalize this. We want to make sure this is good reasoning. And the problem is that nothing we've said so far lets us capture this. Now that's a shame. Wouldn't it be beautiful if we had some machinery to do that? Psst, just to spoil it, that's what we're going to talk about in the second half of the class. So we're going to turn in the second half after the midterm to some machinery that will let us do this. Formalize this chain of reasoning. And in particular, to come back to this, what we'll have when we think about something like FOL is we'll be able to use our different machinery in every case when it says all interpretations and construct single interpretations when it's in this one counter model bit. So these two pieces of kit, interpretations, and just to spoil it, we'll call it natural deduction, on the other hand, are going to jointly then help us be able to do this for any sentence or any collection of sentences. That'll be the tool that'll help us understand validity. That'll be the thing that will get us to entailment, etc. So that's a little setup, I hope, for the second half of the class. But of course, before we get there, we got to go through the midterm. So what we're going to do in the next lecture is just going to be a midterm review. For this, not have to read anything. There is an assignment due. It's important to note that the solutions for these exercises I will post on Canvas. I'll post them in the next few days. So thank you guys very much for this. I hope that you're getting a little bit clearer on how to use interpretations and how to evaluate first order logic. Thank you very much for listening, and I look forward to talking about this material with you soon. Bye.